let's get things going. Full disclosure, I am a high school teacher and I teach grade 12 physics. Yep. So what you're seeing here is a problem that we have left hanging last time we had a class. So this was the same problem that we had yesterday. Player shoots the ball, jumps at a peak height of 2 meters, then releases the ball at a velocity of 8 meters per second at an angle of 55 degrees. We were looking for Y max, hang time, and then range. First things first, we would need to separate the motion into sections. First thing that happened here, player stops, jumps, and then releases the ball at an angle. So what we would want to find now is to determine how high was the peak height of the ball. Initial velocity in y, which is given by v naught sine theta, and then v sub y, or final velocity in y. Then g for acceleration, negative 9.8 meters per second squared, and then t. Since we are dealing with maximum height here, final velocity upon reaching the top is 0. Time is not given. We would be needing this equation. V squared is equal to v naught squared plus 2g delta y. Now delta y in context here, we would be using y max instead. So we will substitute y max for delta y, but still, process would be the same. First step is to know what was the initial vertical velocity, or yung v naught y. And we get that by multiplying the initial velocity by the angle at which the projectile was launched, or the ball was launched. So we have now v naught y equals v naught sine theta, which is 6.55 meters per second. So this is our v naught y. We will be deriving the equation to use. This becomes 2g y max equals v squared minus v naught squared. Then divide both sides by 2g. Cancel this one here. And we will end up with the equation that we will be using, which is y max equals v squared minus v naught squared. V naught y, sorry. Squared. Sorry, I forgot to place the y. So that we would know that it is a vertical direction that we are describing. By 2g. Right. So, substituting the values, we know that since we are at y max, then the final velocity of the object is 0. So we subtract it by the square of 6.55. And all divided by 2 times negative 9.8 meters per second squared. And our answer, let me just type it down here, 2.19 meters. And this is our y max. So that would be here, the position of this ball at this point in time is 2.19 meters. Now, it's essential for us to know that, since we know that the ball was launched at a height, at an angle, it would bear to know that 2.19 is actually not the maximum height. It is the height from the release point. This is the height from the release point. Up to that time, it reaches that peak height. But we are not considering how much or how high the player jumped. So to truly get the maximum height, we must add the height from the release point to the peak height and the 2 meters, the extra 2 meters that the player jumped. So in actuality, if we want to know the height from the ground up to here, up to the ball, then we should be adding 2 meters and 2.19 meters. So that would be our true maximum height. So Y max now would be equal to 2.19 meters plus the 2 meters from the jump, the peak jump. The peak of the jump, sorry. We would end up with Y max equals 4.19 meters. There. So that's our true Y max. So that would be the distance from the ground up to the peak height. The second question is hang time. What does it refer to? It refers to the time from the ball being released up to the point that it reaches the goal for the basket. Going back to my illustration here, my drawing here, you can see that the hoop is 3.05 meters tall. In the first part of the motion, we have a vertical upward motion and a general motion to the right, going to the hoop from the x-axis. At the peak height, since the velocity is 0, it will be the point that the ball will change its motion, its vertical motion from upward. It will now fall. From that knowledge, we could say that at peak height, not only is the upward vertical velocity 0, but it will also be the starting point of our new motion, which was the downward motion. And imagine that this is the start of the motion. So from this point, the ball is now falling towards the hoop, which was 3.05 meters tall. The maximum height. Y max is at 4.19 meters. What we need to figure out is how far will the ball be displaced from the Y max up to this point. So to get that, we simply subtract. We get delta Y. So we make use of our one of the first equations that we used, our discussions. Delta Y would be equal to the final position Y minus Y naught. Now, from what we are seeing here in this situation, our final position would be the position of the ring. So that is our Y, or the final position. Y naught will be the max height, the peak height. So we simply subtract 3.05 meters minus the peak height of 4.19, and that would be equal to negative 1.14 meters. Negative meaning meaning the ball was moving in the negative Y direction. It was falling. This will be our delta Y. So we write down the new given. So we know that delta Y would be equal to negative 1.14 meters. Initial velocity in y, since we are starting at the peak, it should be 0. Then we have v sub y, which was not given. G is negative 9.8 meters per second squared. Then t. That was what we were trying to look for. Now, since we do not have the final velocity here, we will make use of... We will be using equation 2 here. The final velocity is not given. We only know that the ball started from peak height at 0 because that was the beginning. But we don't know how fast the ball was moving after that. Delta y would be equal to v naught t plus 1/2 g v naught y t is gt squared. Here, this expression here, v naught y t, is actually 0 since v naught y is 0. So what we will be using as our formula would be delta y equals 1/2 gt squared. Okay, now let's substitute for a bit. Sorry, not substitute, but derive the equation. We multiply both sides by 2, so we end up with 2 delta y equals gt squared, and then divide both sides by g, and then get the square root of both sides, and then we will be having this form of the equation. So how much time? Let me just calculate. Square root of 2 times negative 1.14 divided by negative 9.8. And our answer is 0.48 seconds. So that here, that time is from the peak to the rim. Okay? So that's how long it took the ball to reach the goal. To go back to the range problem, delta x would be the unknown. It's what we were looking for. We now have v naught x, which will be given by v naught x equals v naught cosine theta, and then we might need to figure out what is the time from the release point going to the peak height, because the release point and the height of the goal is not the same height. So we must find out first the time from the release point to the peak height. Anyway, let's just get on with it. So we use the same given. We know the displacement. Delta y would be 2.19 meters because that is the distance from the release point to the peak height. V naught y, we will use the same, which is 6.55 meters per second. Okay. Then Vy is 0. G is negative 9.8 meters per second squared. And then time is missing. I think we can go with equation 1. It's the easiest, right? Yeah, I think we can just go with equation 1. So that would be V naught. V is equal to V naught y, or Vy equals V naught y plus, what was that again? 80 or GT. Yeah. So we move things around and we get T is equal to V naught, V minus V naught y over G. Substituting the values, we get 0 minus 6.55 meters per second divided by negative 9.8 meters per second squared. And our time 0.67 seconds. Now, what do we do with this time? What do we do with this time? We add it with the one that we have just calculated here. Because it will be describing the time when the ball was released from that 2-meter point up to reaching the peak height, and then from the peak height going to the rim. To get time, for us to really determine the range, then time would be calculated using this. T would be equal to the time from release to peak. Let's just put that there as a descriptor, right? So time from release to peak height plus the time from the peak to the hoop. Again, since we have computed the time already, that would be 0.67. This is the time from the release point to the hoop. To the peak, plus the time from the peak to the hoop, which was what again? 40.48 seconds. Sorry if I move around so much. So this is not entirely a professional setup at all, but hey, it worked. So again, 0.67 plus 0.48 is about 1.15 seconds. And that would be the time we can use to determine our range. The motion of this object changes as time goes by. So we must take note of what is happening with the object. For example, there was a change in the direction in the vertical motion, right? Kasi galing dun sa peak, it would stop climbing and begin descending. Going back to what I was saying, we were in the middle of calculating the range. So again, delta x, di natin alam. V naught x equals, let's just calculate that. That would be 8 cosine theta, cosine 55, which is equal to 4.59 meters per second. Yung final velocity at peak height also serves as the initial because there was a change. Nandun na yung change eh. From going up, it stopped, then it started to fall down. So it started at 0 as it begins to fall towards the hoop. Okay, so range. So V naught x and then V naught y, Vx. Since we are dealing with horizontal motion, it is already known that V naught x and Vx is the same because horizontal motion is constant. Horizontal velocity is constant, in the x-axis. Then time, we would be using our calculated time of 1.15 seconds. And we can simply go about this problem just like what we have for a simple velocity equation. And what we will be having now is delta x equals v times t, which is the average velocity of 4.59 meters per second multiplied by time of 1.15 seconds. And we'll find out that the player was how far? At 5.28 meters away from the hoop. So, to put things in context, iano natin yung final diagram natin. Let's just draw draw the picture again so we would get the final details of our problem. So this is 3.05 meters. The range from here to the player, so delta x, or the range, was 5.28 meters. So again, yung height ng jump, peak jump, was 2 meters. Initial velocity of 8 meters per second. Theta of 55 degrees. Peak height from there. So Y max natin was at 4.19 meters. There you go. Then time from peak to height. From release to peak was about 0.68 seconds. Time from peak to hoop was 0.40. I forgot again. 48. 67 pala. Sorry. And 67. Then 0.48 seconds. And then time from release to hoop, the final time that we would using for range would be 1.15 seconds. And there you go.